Okay, 2.1 part 1, there's a ton of stuff in this section. So take out a notebook to write some of this stuff down. So we'll start off with an example. My little sister Savannah is 3 years old. She has a piggy bank she wants to fill. She started with 5 pennies, and each day I come home from school, she is excited when I give her 3 pennies that are left over from my lunch money. Use a table and an equation to create a mathematical model to represent the number of pennies Savannah will have on day N. So first of all, let's just talk about some important stuff. So it says she started with 5 pennies. That's important. And she's excited when I give her 3 pennies that are left over from my lunch. So every day she's getting 3 more pennies. This is kind of review from Module 1. So I kind of filled out the table for you. So she started with 5 pennies. So we're starting at 0, 5. And every day you're adding on 3 pennies. So on day 2, she would have 11 pennies. And day 4, she would have 17 because we're adding 3 pennies per day. Okay, so there's a table. The third and fourth column, we've been working with that, and then we've been kind of trying to do it without it. So it's here if you need it, but let's talk about the recursive formula. So f of n equals f of n minus 1 plus blank. So what are you doing to the previous one to find the next one? Well, we're adding 3 pennies, and we started at f of 0 equals 5 pennies. So we got our recursive formula. Our explicit formula, it started with 5 pennies at day 0, and you're adding 3 pennies. So remember, when you're adding repeatedly, that's multiplication. So 3 times the number of days that go by, and then the 5 pennies that she had originally. You can also see that in the fourth column, that the number of times you add 3 is the same as n. So is this arithmetic or geometric? It is arithmetic. Okay, so this is all review from Module 1. So let's start looking at some of the new stuff. So this is that same problem graphed. So it starts out here. She starts out at day 0 with 5 pennies. And I know that there's no scale here. You can't see that this is at 8. But at day 1, there are 8 pennies. So this point right here means that at day 2, there are 11 pennies. This is all still she has 11 pennies. Okay, here's where it starts to get a little different. So this is all still review. We know how to read points from a graph. Will the number of pennies change between the days? So I want you to think about, okay, she started out with 5 pennies. Her sister comes home from school the next day and gives her 3 more pennies. Will the number of pennies she have change while she's waiting for her sister to come home the next day? Or does she have to wait until her sister gets home to get 3 more pennies? So the answer here, she has to wait a whole nother day to get more pennies. Her piggy bank is not getting any changes in between the days. She has to wait till her sister gets home. So we're going to say no, the number of pennies does not change between the days. Probably thinking why does that matter? This is a new concept, okay? So this is brand new in Module 2. We've never talked about this. Problem number 1 that we just looked at is an example of a discrete function. So there's 2 ways to think about if something's a discrete function. So one way, this is kind of the easier way, I think, is where you think about if the data is just countable. So think about if she has to say how many pennies she has to count how many pennies there are in her piggy bank. Another way to think about it is what we were just talking about. If nothing is happening between the X values or the inputs, so if you go back to here, nothing was happening. She was not gaining any more money until the next day. So that's another way to think about it. So you should write this down, this definition down into your notes, because this is a new concept in Module 2. One thing I want to note as well is that because nothing's changing in between the days, with a discrete function, we do not connect the points. So your graph should be just isolated points, so not connected with a line. Okay, so another new concept. Well, it's kind of new, but we've actually been working with this all along. We already talked about the fact that this example here is an arithmetic sequence, okay? So we already talked about the fact that it's arithmetic. All arithmetic sequences can also be called, they're also linear functions. So all year we've been working with linear functions. We just haven't been calling them linear functions. So what is a linear function? It's a function where there's a common difference, so a number being added repeatedly or subtracted repeatedly. And that could also be called a constant rate or the slope. So here's an explicit formula that we just wrote. This is actually also a linear function. Even though it's an arithmetic sequence, it's a linear function as well. We can see in the table that this is being added by 4 here. So that's a linear function because we're adding repeatedly. And when you're adding or subtracting the same number over and over again, you get that straight line when you graph it. So this, even though it's not really new because you've been doing it all year, but we haven't used this terminology yet. So I would write all this information down into your notebook. So you can pause the video and write it down, and then when you're ready, we'll move on. Okay, so what's the connection between what you've already been doing and what we're trying to teach you now? Okay, so we've been working with arithmetic sequences all school year. Arithmetic sequences are always discrete. So everything we've done in Module 1, those were all examples that were discrete, okay? Arithmetic sequences are a small group of a larger group called linear functions. So if you think about it, I always in my classes use this example. So think about like dogs. Dogs is like a big group of animals. There's lots of different kinds of dogs. A little subgroup of dogs is a terrier. I think that's spelled right. So there's a kind of dog called a terrier. Okay, that's a kind of dog. All terriers are dogs, but not all dogs are terriers because there's other kinds of dogs. So it's the same thing with linear functions and arithmetic sequences. All arithmetic sequences are linear functions, but not all linear functions are arithmetic sequences. So I would draw this in your notes and we'll actually add to it later in the slide. So you can pause the video if I can get rid of this dogs. Oh my goodness. Go away, dogs. Okay. Whew. Okay. So moving on. Let's look at example 2. So our family has a pool for relaxing in the summer. That sounds nice. The pool holds 1,500 gallons of water. I decided to fill the pool for the summer. When I had 5 gallons of water in the pool. So there's already 5 gallons of water in the pool. And she decided that she didn't want to stand outside and watch the pool fill. So I had to figure out how long it would take so that I could leave, but then come back and turn off the water at the right time. I checked the flow on the hose and found that it was filling at a rate of 2 gallons every minute. Use a table, graph, and equation to create a mathematical model for the number of gallons of water in the pool at T minutes. So it says here the pool already had 5 gallons of water in it. And she figured out, okay, 2 gallons of water. If you put the hose in the pool, 2 gallons of water will go into the pool every minute. So I kind of filled this out because, again, this is review from Module 1. Starts out at 0.5 because it was there before she started. And then 2 gallons get added every minute. So we can just fill this in. I think we all know that would be 11. This would be 15. I'm not going to fill in the third and fourth column because, like I said before, we're trying to we always can use the third and fourth column. We could always draw it if we want to. We know how to do that. But we also want to start trying to do, write these formulas without them. So let's take a look at a recursive. We're taking the previous one and we're adding 2. The starting value is 5. If we go to write our explicit formula, we have 5 plus 2. And we're going to use just a t because it starts at 0. So if you notice, it's the same as t. And I'm using t because they said t is for time. So n or t, it doesn't matter. This problem just happens to use t. Okay. Is this arithmetic or geometric? Since we're adding, it's arithmetic. Okay, if we scroll down, here's the graph. It starts at 5 gallons, and then every minute, you'll see that 2 gallons are in the pool. So here's the new thought. Will the amount of water change in between the minutes? So I want you to just visualize a hose going into a pool. Think about does the water just automatically just dump into the pool every minute, 2 gallons? Or is it kind of gradually going into the pool? So when you have hose going into the pool, it gradually goes in. So between 0 and 1 minute, the amount of water in the pool is actually going to be changing. So this is a yes. So that's why the points are connected, because there's actually the amount of water in the pool is changing in between the points. So this is an example of a continuous function. So a continuous function is where the data is measurable. So think about that pool water. You can't count how many gallons. You have to measure it. Okay, so you're going to measure how many gallons. Also, another way to think about it is something is happening between the x values or inputs. So in between 0 and 1 minute, the pool is still filling, even though we know that at 1 minute it'll be 2 more gallons. Couple things about this. Since there's no clear previous value, because it keeps changing every millisecond in here, we can't really use a recursive formula. So we should actually take this away, because you have to take the previous and do something to it when you have a recursive formula. And also, we connect the points with a continuous function. So go ahead and pause the video and write this definition down. Okay, and then the last thing, where does this fit in with the whole scheme of linear functions? That should not say linear, sorry. But a continuous function is also a linear function, or linear functions can also be continuous. But if they're continuous, they are not arithmetic sequences, because all arithmetic sequences are discrete. So I would add this to your oval. And that is actually everything in 2.1 part 1. So you learned about what is discrete. So discrete is when it's countable or something is not happening in between the x values. You learned about continuous. That's when the data is measurable and that there is something happening in between the x values. And then the last thing is you've learned that we've been working with linear functions this whole time. We've been just working with a small group of them called arithmetic sequences. So that is everything you need to know. Make sure you can go back in this video, you can pause and write down everything so you have it in your notes.